Here are some more problems to solve. So I took some advance. So the question is again, use elementary row operation and Gauss-Jordan method to solve the following system. So when I'm lazy, I just say solve the system. So you know that you need to use elementary row operations and Gauss-Jordan method. That's the only method we know, and the elementary row operations are the only operations allowed. So I have the following linear system. It has three equations with three unknowns. I write augmented matrix for it. So for the first equation, coefficients are 1, -1, 2, and on the other side is 3. So 1, -1, 2, 3. The second equation, 1, 2, -1, on the other side, -3. The last equation, there is 0 in front of x1, be careful. So it's 0x1, 2x2 minus 2x3, da-da-da. The other side is 1, cool. Now what I want is to use elementary row operations. The one that we use the most is the replacement, but I need to use it smartly. And Gauss-Jordan tells me how to use it smartly. I need to produce zeros beneath my leading entry. And ideal leading entry is 1, so you fight to get 1 in the corner. And then once you have it, but in our case we have it by default, we need to introduce 0 here. How do we do that? We replace row 2, this is called row 2, by row 2 minus row 1. If I do that, I'll get 0 here. So row 2 minus row 1 get 0, row 2 minus row 1, so 2 minus 1, so 2 plus 1 is 3, -1 minus 2 is -3, and -3 is -6. Gorgeous. And then I copy row 3. Beautiful. And then I say, wow, look. I have 3 minus 3 minus 6. So if I divide row 2 by 3, I'll be a happy man. So that's what I do. I divide row 2, I replace it by 1/3 times row 2. So row 1 and row 3 stay the same. So copy paste. Then I have 1 minus 1 minus 2. Yes. Because my Gauss-Jordan likes to have 1 as my leading entry. So now I need to produce 0 below. Cool. How do I do that? Well, I replace row 3 by row 3 minus 2 times row 2. Yes, sir, do that. Compute, that I verified it. It's true. So these are the results I get. 0, 0, 0, and on the other side, 5. And you go, wait a minute. The last equation says that 0 times x1, which is 0, plus 0 times x2, which is 0, plus 0 times x3, which is 0. So 0 plus 0 plus 0 is 0. So 0 is equal to 5. No, sir. That's a contradiction. It's false. It's not true. So the last equation tells me that there's a problem in this system from day one. But we couldn't see it. But thanks to elementary row operations and Gauss-Jordan method, now we know there's trouble in paradise. This system has at least one of the equations that is in contradiction with others. What does that mean? We remember that each equation puts constraints on variables x1, x2, x3, which means that at least one of them is not compatible with the other two. Aha! That's why there is no x1, x2, x3 that could satisfy the system, because somebody here is crazy, asking for crazy stuff. So the last equation tells me that there is a contradiction. That means that this system doesn't have a solution. Well, guess what? The solution set for this system is the same as this one. So this guy doesn't have a solution. While the solution set for this guy and this guy is the same, so this guy doesn't have a solution. Guess what? Solution set for this guy and this guy is the same, so this guy doesn't have a solution. How do I know that? Well, elementary row operations guarantee that solution sets are the same throughout the process. So if I don't have a solution for this guy, I don't have a solution for anybody in between, including the original system. Ta-da! Beautiful. So whenever you have this, you know you have a problem. Now, a note, if this instead of 5 was 0, well, there's no trouble. 0 is equal to 0. You just keep going. What that would mean is you have one of the equations that is repeated for nothing. But we will see that later on, eventually. But if you have 0, 0, 0, 0, slash any number different from 0, bye-bye, there's a contradiction, system doesn't have a solution. Yes, sir. So now try another system to have some fun. So I change the system. Let's take something easy. Okay. So I have x1 plus 2x2 plus x3 equals 0, all beautiful, and x1 plus x3 equal to, thank you, and then x2 plus 2x3 equal to 1. Gorgeous. So write augmented matrix form, we'll do that. So all this is useless now. Ta-dam. All this goes. So you see some systems, they just don't have solution. What can you do? So we have 1, 2, 1, 0 on the other side, 1, 0, 1, 2 on the other side, and 0, 1, 2, 1. Okay, cool. Again, we are lucky, we have our leading entry 1, yay. So row 2, now we want to introduce 0 here, replaced by row 2 minus row 1. So row 1 stays the same, copy paste, row 3, well, it's already 0 there, yes sir, no need to do anything. So row 2, 1 minus 1, 0, 0 minus 2, minus 2, 1 minus 1, 0, 1i, 2 minus 0, 2. Ah, beautiful. Ah, look at this. So I have my leading entry and zeros below. Good job. In the row 2, leading entries is minus 2. But I see, it's 2 here. So I could actually divide by negative 2, and I'll get 1 here. And then my Gauss Jordan will love me. So that's what I'm going to do. Replace row 2 by minus 1 over 2 times row 2. Boom, boom. So row 1 stays the same, didn't change. Row 3 stays the same, didn't change. And row 2 now is 0, 1, 0, minus 1. Be careful with the signs. Why did I choose minus 1 over 2? Well, I had minus 2 here. What I want is leading entry equal 1. It's very useful. So now you see, it's beautiful. I can kill this guy here. So I have my leading entry, I want to introduce zeros below. So row 3 replaced by row 3 minus row 2. So row 1 doesn't change, copy paste. Row 2 doesn't change, copy paste. Be careful. And then 0, 1 minus 1, 0, 2 minus 0, 2. And then 1 minus minus 1. So that's 1 plus 1, that's 2. Ah, that's beautiful again. So I can divide again by 2. So row 3 replaced by 1 over 2 times row 3. So then I'll get 1 here, and Gauss Jordan will love me for that. 1, 2, 1, 0, 0, 1, 0, minus 1, and then 0, 0, 1, 1. Da-da-da. Beautiful. So I have my leading entry, 0 below. Row 2, boom, hit the leading entry, 0 below. Good job. Third row, hit the leading entry, there's nothing below. And you see the staircase, tag, 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 staircase. It will be important later on. That's how we find echelon form. So this is echelon form of a matrix. And later on, we are going to produce reduced echelon form. That's what our Gauss Jordan tells us to do. How do I produce a reduced echelon form? My leading entries are 1, and then I need to produce zeros above also. So I have zeros below, I need zeros above. So I need to kill this guy here. How do I do that? Replace row 1 by row 1 minus row 3. It's beautiful to have these leading entries 1. It's gorgeous. I'll try to save some space. So last row doesn't change. Second row, no need to change. Minus 1. It's just the first row. So 1, 2. So this minus this is 0. Obviously 2 minus 0 is 0. Now I have 0 minus 1 is minus 1. Just one note. when you produce zeros below, you don't want to destroy them. Okay? You keep your zeros. We love them. Now, I have my leading entry and zeros above and below. Okay, below there's nothing. I have my leading entry, zeros below. Cool, there's nothing above. Leading entry, there are zeros below. Good job, but I need to produce zeros above also. So I need to kill this guy. So I take row 1, replace by row 1, minus 2 times row 2. Ta-da! Let's do that. So last row doesn't change. Second row doesn't change. First row, changes. So 2 minus 2, 0, 0 minus 0. So look how easy it is to compute. So let's just write it cute. And then I have minus 1, minus 2 times minus 1. So that's minus 1, minus 2. Ooh, minus 2 is 2. So minus 1 plus 2 is 1. Yes, sir. Hey, look at this. This is my reduced echelon form. It happens to be identity matrix 3 by 3 also. Gorgeous. And this is when I stop. Gaussian tells me when you get your reduced echelon form, stop. How do I know? Well, leading entry 1, zeros below and above. Leading entry 1, zeros below and above. Leading entry 1, zeros below, okay, nothing, and above. Cool, good job. So this means that x1 is 1, x2 is minus 1, and x3 is 1. Yes, sir. So I have a unique solution. So its solution is all about variables, x1, x2, x3. So here, x1, minus 1, 1. Yes, sir, unique solution. Fantastic work. All happy. Okay. Nice. So let's go for last one. And this one, okay, this one is happy guy. Okay, so we have x1 minus x2 minus x3 plus 2x4, apply 4 variables, equal 1. And we have 2x1 minus 2x2 minus x3 plus 3x4 equal to 3. Okay, and the last one, where are you? I have too many things written up. Okay, well, minus x1 plus x2 minus x3 equal to minus 3. Need to be careful if you make an error here while everything else is wrong, so you just suffer for nothing. So you need to pay attention at every single step. So that's the secret. How do I know it's correct? Well, when you have a unique solution, what you could do is just plug it back to your original equation and see if it satisfies the equation. That's easy. But what happens if it doesn't? Well, that means you made an error somewhere. Well, good luck to find the error. Waste of time. So how do we prevent problems? Well, by checking each operation as it happens. Double check your computations as you do them. So here, augmented matrix, make sure you do it right. Pay attention. Slash. Okay. Double checking. It looks good. Okay, so that's how I do. I double check and I know now this is correct. Okay, let's start working. I need to produce 0 here. I have my leading entry 1. Yes, sir. Produce 0. Replace row 2 by row 2 minus 2 times row 1. Beautiful. So copy carefully row 1. Tuck, tuck. So row 2. 2 minus 2, 0. Okay, let's put some Okay, minus 2 plus 2, oops, 0. Oh, that's nice. So minus minus a plus, that will be beautiful. This minus minus, so plus, so this is 1. And then 3 minus 4 minus 1. 3 minus 2, 1. Okay, cool. Double check. Should be correct. 0. So this one also. And this one is plus 2 minus 1 is 1. And then 3 minus 4 is minus 1. And 3 minus 2 is 1. Good. Now I need to produce 0 here. So I replace row 3 by row 3 plus row 1. Beautiful. So this is 0. So I add them. Oh, 0. I add these two. So this is minus 2. Be careful. And this is 2. And this is minus 2. Ah, beautiful. So I can produce, I can divide by minus 2 everything. So row 3 replaced by minus 1 over 2, row 3, because this will give me 1, 1, 1. Yeah. I'm very happy. Copy carefully. Oops, copy carefully. Zero, 0, 1, minus 1, 1. And now here is 1, minus 1. Be careful with the signs. 1. Okay. Well, look at this. So I can now work on row 3. I need to, so I have my leading entry zeros below. For the second row, boom, a leading entry here. I need to produce zeros below. I need to kill this guy. So I replace row 3 minus row 2. Subtract them, it's gonna work. So first row again, copy paste. Second row stays as it is. Don't touch it. Don't mess it up. Last row. So I have zeros. So now it's this minus this is 0. This minus this. So minus 1 plus 1 is 0. And 1 minus 1 is 0. Ah, beautiful. So the last row says 0 is equal to 0. Okay, I know that. So there's no contradiction here. Huh? So 0 is equal to 0, we know that. So there's no contradiction. What does this mean? Well, we are happy, that's fine, but what does this mean? That means that in my system, there is one equation that is redundant, which means I don't need it. But when I look at my system here, I don't know which one I don't need. Okay? We couldn't guess that just from looking. This process helped us realize, hey man, you have one equation in your system that is useless actually. You're repeating the constraint for nothing. Well, we didn't know that. It's fine. Thank you. Happy. We go on. So I have my leading entry, zeros below. Leading entry, zeros below. Now I need to produce zeros above my leading entry. That's what my Gaussian says. What happens with this column? Nothing, I don't care. This one has leading entry. That's what matters. I need to produce zeros above leading entry. Because this row doesn't have leading entries. 0 is never leading entry. Anything different from 0 is leading entry, but 0 is not. Okay, cool. So this column contains leading entry. I need to kill this guy. Fine. So row 1 is replaced by row 1 plus row 2. Fine. Let's go. So row 2 and row 3, they don't change. Bad news, you need to copy still the row 3. Okay? You cannot just dump it. You keep it there. So this plus this, 0. This plus this is 1. This plus this is 2. Okay. So now I look and I say, hey, leading entry, zeros below. Leading entry, zeros below. Leading entry, zeros above. Good job. Leading entry 1, good job. This is reduced echelon 4. It's called the reduced row echelon form. Well, I just dumped the row, I know it's full. So it's reduced echelon form. Yes, sir, now I stop. This is when my algorithm tells me, Gaussian says, when you produce reduced echelon form, you stop, sir. Okay. Now, write this in terms of a system. Write the corresponding linear system. I don't need to keep repeating linear because all our systems are linear. Why do I do this? Well, I'm done here. I want now to figure out what's the solution. Well, I need to find expressions for x1, x2, x3, x4. Yes, sir. So x1 is main variable, x3 is main variable, because in those columns I have my leading entries. Which means that x2 and x4 are free. Cool. So let's just write these things and it will be obvious. Plus x4 equal to. So these pivot columns or leading entry columns, they tell us which variable is main. So x1 is main and x3 is main because column 1 and column 3 have leading entries. And column 2 and column 4 are for free variables. x2, x4 are free. Yay! So now I have x3 here minus x4 equal to 1. After that is 0, 0 equals 0, doesn't matter. So from here, I need to write an expression for x1 and expression for x3. Okay, x1 is 2 plus x2 minus x4, yes, and x3 is 1, so write it plus x4. Be careful with the signs. x2 and x4 are free variables, which means they can take any value. What does that mean? Well, our system will have infinitely many solutions. So let's write the solution for our system. Ta-da. Okay, hence a general solution of the system, actually for all systems, the first one and every other system in between that we computed is, so solutions about unknowns, so it's x1, x2, x3, x4, that equal. So x1 is that expression over there, 2 plus x2 minus x4. Okay. x2, well, x2 is free variable, we keep writing x2. x3, well, there is an expression for x3, 1 plus x4. And x4 is free variable, we keep writing x4. How do I know it's free? Well, they are on the other side, as we said. So x2 and x4 are free variables. So the system has infinitely many solutions. So original system and all other systems that we got through the process, they all have the same solution set given by this, and there are infinitely many solutions. So you can say, hey, it's a lot of infinitely many because you can vary this guy and this guy. Wow, amazing. So that's how we do it. Practice, practice, practice. More you practice, better you become, faster you solve it. It is important to go from your reduced echelon form back to the system and then take your main variables and identify your free variables. Rewrite this because this will be useful now to write the solution. That's why we do all this, to be able to write the solution vector. Our free variables x2 and x4. Why is this ugly? Gorgeous. x2 and x4 are free, they stay as they are, and x1 and x3, they have expressions for themselves. Okay, so each time you pick different value for x2 and x4, well, x1 and x3 will change accordingly. All right, practice, practice, practice.